Thevenin, which then tells me that the resistor drops out, and I just got that voltage source. So if I calculate that voltage, I get this. From that voltage, I then go in and I simply apply Ohm's law twice. Now, you ready to do this for Thevenin's? Again, brace yourself. Let's see. Right? For y'all node equation lovers, you're gonna like this. So we should redraw the circuit here. So now we want to do node analysis. So if I redraw the circuit here, this guy's 10K, 30K, 10K, 30K. Then we come down here. And then I have a resistor here. So then this becomes, I think this is a 10K and a 30K. And then this is, of course, the So the only thing different that I'm going to calculate here, I'm really calculating voltages because the current just sort of like just happens, right? Because it's just going to be an application of node analysis here. So what I'm going to do here is that let's start drawing my nodes here. So if I look at this thing here, I don't count this node right here, but let's just start drawing them. So this node here, just from hindsight, I'm going to call that V1 since I called that V1 right there. And then, actually, let me not call it 1. Just because I think I'm going to avoid applying V1 and V2, and I'm going to have a tendency to immediately apply V1 and V2. So I'll call these A, I'll call this VB, I'll call this VC, and then I call this VD here. I'm afraid that if I call it V1 and V2, I'm immediately going to go to simple circuit. And I really don't want to do that. So what I'm going to do here is that I'm going to start counting here. So what you find here is that I have how many nodes? Well, I got VA. I can connect VA to V out. No, I'm not counting this as a node. It's not part of the node, right? That's the value of the voltage source. So what I'm going to do here is that I count, what, 1, 2, 3, 4. So I have 4 nodes, and then I have 1 source, so that gives me 3 node equations. Okay? So if I look at this, what am I seeing here? Well, that means when I look at my nodes, I have what? I have a node VA, I have node VD, and then I have a supernode between V and C, which then immediately gives me a supercondition between V and C. And then I have sort of like the ideal conditions. And the ideal conditions will really connect V1, V2, and VD. So what you're seeing here is I got 1, 2, 3, 4, 5. So I have 5 equations, 5 unknowns. So let's start writing them. So the first one that I'm going to look at is I'm going to look at node A. Okay, so if I look at node A, I have 1, 2, 3. So if I write that, I have, so look at that, I have 2 10s, 2 30s connected to node A. So I'm going to write, just to simplify this, I'm going to write it like this. Okay, so then I have 10 with the ground, I got 30 without, with V out, and then I have 10 with B, 30 with C. So then I'm going to get minus 10 VB minus 30 VC equal to 0. Okay? So now the next node I'm going to go after, I'm going to go after node BC. So I got to write the super node. So if I write the super node here, what you're finding here is that I got to combine these two nodes. So here I go. So for node B, you can see that I have 10 plus 30 VB. Then I got two mutuals. I got minus 10 VA minus 30 connected to VD. So that's my node B there. So now if I focus on node C, I'm going to then go in and I'm going to go, I have 30, 10 VC, then I have the mutual with the A, which is a 30, and then I have the 10 connected to VD here. These equations are coming out nicely, aren't they? Nice and long, the way you like them. Right? When you're doing this super node here. So then if I look at the connection between these, I get VB minus VC equals 6. So I got 3 of the nodes. So now I got to erase here to make room here. But, you know, intuitively, this is already much easier. Right? Unless you like turning your brain off and not thinking very much. Yeah, I'm not going to say any names. Is that what you mean? So then I have node D. Here I go. Node D here. And when you look at node D, you find that there are 2 resistors connected to this. So node D says that I have what? 10 plus 30 VD. Then I have mutuals where I have 30 connected with VB. Then I have 10 connected to VC equals to 0.
So for node A, you accounted for 2 of each.
2 of each because I have those 4.
Oh.
So now I have the ideal conditions. So if I look at the ideal condition, it says that VD must be the same as VD equal to 0 here. Right? So we say here that V1, V2 must be the same, so they got to be equal to 0. So that node must be the same as this node, which is this guy equal to 0. So now what am I going to do? I'm going to matrix this guy up. But probably the first thing to do here is that I'm going to come back and I'm going to set VD equal to 0. Right? Now you could just put this into your calculator as that being one of the elements here, but let's check it out. Look what happens. Look, this term is out. That's 0. This term is out. This term is out. And that's that. So now, I matrix this guy up. Okay? So now if I put this into a matrix, I'm going to say that you're going to get the solution of VA. In the end, you should get an equation that essentially tells you, how about if I not matrix this guy up? How about if I just give you the answer? Since we know that what we're going to get here, you're going to get that V out is equal to 12 volts. And if you get that to 12 volts, then that means I can then calculate the current just like we did before, where we just look at the circuit, and that's what we have. So you would get VA and V out there, and that's where you're at. So all I did here was just set it up for you. I didn't actually solve it here. So what do you think? Would you prefer this technique? Or would you prefer that technique? Of course you're not going to raise your hands, because I'll call you out by name when you start to do that technique over there. By the way, they're both legit, of course. It doesn't really matter, right? If you see this way, that's the way you should do it. If you see this way, this is the way you should do it. Okay? So now let's get into a little bit more shady of a circuit. By the way, I'm almost done with this chapter. And I'm almost done with this. Okay, here we go. Let's look at this circuit here. Okay, so what are we solving for? We're solving for V out, and we're solving for the current going in. I think let's do this with using simple circuits, and then we'll do nodes as well. See if you can think your way through this thing. By the way, at the end of class, I have to leave immediately. I'm giving an exam at 4 a.m. So we want to, I told them that I would start the exam at 11 o'clock. So I'm going to leave ASAP. Let's rock this one out real quick. Okay. So the first thing I'm going to do here, I'm going to use simple circuits today. So when I look at this thing here, there's a lot of ways of doing this thing. Probably the very first thing that I would do is I would do a source transformation. If I do a source transformation, note that I can make this into a current source, and then back to a resistor, then it's back to the original circuit. Okay? So I would say that the easiest approach is source transformation.
Carlos,
Yes.
are source transformation valid on simple circuit type like questions on the exam? When you say
Absolutely not. Not on the exam. And you'll see. I'll say if you do something different than what I list, I give you 0. And I have no problems giving you 0 on an exam problem. Damn, that's gotta hurt, right? That's 20% of the grade. Don't do something silly like that. Right? But this is chapter 6, which is very different. Okay? Now, don't make me hurt you, right? I don't want to hurt you. So then check this out. Let's draw the picture real quick. Look at this. This and this would give me a 2 amp. With the 6 and 6 in parallel is 3. So I got 3. And what did I say? 2? So 2 times 3 is 6. So I get a 6 volt. And then I get a 3, and then I add that. So then I get this circuit right here. I get 6 volts. I get 9K because I get a 6K plus a 3K. And then this is 6K right here. So look, ground, that means current's this way. So what is that? 6 divided by 9, is that 2/3? So 2/3 current goes all the way down to right here, and then it splits. You could do that, but let's not do that way. But that would be my first choice for solving this circuit. So let's say that you don't see this. What now? Then go back to the original ideas. Okay? So the original idea here is that you know that this guy here is what? That's 12 volts. You know that the current here is equal to 0. So you know that the current's coming this way, then it looks like there's a branch off there. But there's something really interesting about this circuit. Check this out. This resistor is connected to the ground. This resistor, look at this, also connected to the ground, right? If that is ground, this is ground, so I can immediately come in and I could just say ground. But if that's ground, note that this resistor and that resistor are in parallel. Right? And if they're in parallel, then that means here that I could go in and I could just start looking at the current. What's happening? This current is getting split right here. So do I know the current across here? Yes. Because if I do that, what I want you to realize is here is that said that note 2 6K ohm resistors are in parallel. So if I draw these out, that really means that I'm really looking at this kind of circuit here. I got a 6K, and I got another 6K, both connected to the same ground. So if this is 12 volts, this is 6K, this is 6K, this is 6K. If I figure out the current in this branch right here, then that means I know the current here. Okay? So let's solve this here. So what I want to look here is that I want to solve for this current I across that 6K right there. So if I do that, that current across here, note that the voltage divider of the 6K has to be that it's 6K times I 6K. But this guy has to be what? 3 divided by 6 plus 3 times 12. Okay, help me out with the numbers. I'm getting too old. 36 over 9 should be 4 volts. Right? So if this is 4 volts, then that means that the 6K current must be 4 divided by 6, which is 2/3 of a milliamp. By the way, which we knew immediately when we did this guy right here. So there's the current. So what is that current doing? That's the current here. Right? That's the current there. So follow the current. Right? The current comes here, it splits. As it splits, 2/3 goes this way. Now, there's no current going down, so that means I still have 2/3 going that way. So look, if that's ground, then that output voltage better be negative, because current always flows from a high to a low. So then if I come in here and I solve it, so look, I'm going to squeeze it right into here. So if I do that, then that means here that then I have, so now I look at that current here, look at that resistor right there. So then it's what? 0 minus V out has to be what? 6K times the voltage here times the current here, so it's got to be 6K times 2/3 milliamps. So therefore, V out has to be 12 divided by 3. It's got to be negative 4 volts. Damn, isn't that cool? There's a lot of ways to do this. I would have picked this one. I think it's just way easier. But if you don't see it, still come in and just say, okay, 0, that voltage must be the same. 2 grounds, so therefore they must be in parallel, so it must be like this. So then I come over here, and then I just apply that. Why do I like this? Because I feel like I know what the hell is going on in the circuit. Whereas the node, do you understand what's going on here? No, you're just writing, right? You're just writing. It's like when you get the algebra and you know what to do, you just go. This way you're going like, okay, what is the current doing? Okay. Yes. I don't know. I think I said it after spring break. I can't remember what I did. I think I changed it online. I may not have, but okay. I'm gonna take off. I got